NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve the equation open parenthesis x plus 2 close parenthesis to the fourth plus open parenthesis x plus 5 close parenthesis to the fourth equals 17 using a symmetry-based substitution. We'll center the two bases around a single variable y to make odd powers cancel cleanly. Step 1. Define y as the average of the two bases, x plus 2 and x plus 5. That is, y equals the sum of x plus 2 and x plus 5 divided by 2. This gives y equals 2x plus 7, all over 2. Solve for x. 2y equals 2x plus 7, so x equals the quantity 2y minus 7, all over 2. To see the symmetry, notice that substituting x equals 2y minus 7 over 2 turns x plus 2 into y minus 3 halves and x plus 5 into y plus 3 halves. These are symmetric around y. We'll draw a simple number line showing y in the middle, with y minus 3 halves on the left and y plus 3 halves on the right. Now substitute into the equation. Open parenthesis y minus 3 halves close parenthesis to the fourth plus open parenthesis y plus 3 halves close parenthesis to the fourth equals 17. Step 3. Expand each fourth power using the binomial theorem. Because these two terms are symmetric, the odd power terms cancel out, the y cubed and the y terms vanish. We are left with 2y to the fourth plus 27y squared plus 81 over 8 equals 17. Multiply by 8 to clear fractions. 16y to the fourth plus 216y squared minus 55 equals 0. Step 4. Let z equal y squared. Then we have 16z squared plus 216z minus 55 equals 0. Compute the discriminant. 216 squared plus 4 times 16 times 55 equals 50,176. The square root is 224. So z equals negative 216 plus or minus 224 all over 32. That gives z1 equals 1/4 and z2 equals negative 55 over 4. We discard the negative value for real numbers since y squared cannot be negative. Step 5. From z equals 1/4, y equals plus or minus 1/2. Convert back to x using x equals 2y minus 7 over 2. If y equals positive 1/2, x equals negative 3. If y equals negative 1/2, x equals negative 4. Therefore, the real solutions are x equals negative 3 and x equals negative 4. Welcome! In this example, we will solve the quadratic equation using grouping and factoring. Example: solve the equation 2x to the fourth minus 5x cubed plus 5x minus 2 equals 0. Step 1. Group terms to reveal common factors. We will group the terms with coefficient 2 together and the terms with coefficient 5 together. That gives left parentheses 2x to the fourth minus 2 right parentheses minus left parentheses 5x cubed minus 5x right parentheses equals 0. Step 2. Factor out the common numbers in each group. From the first group we factor out 2, and from the second group we factor out 5x. We get 2 times left parentheses x to the fourth minus 1 right parentheses minus 5x times left parentheses x squared minus 1 right parentheses equals 0. Step 3. Use the difference of squares on x to the fourth minus 1. Since x to the fourth minus 1 equals left parentheses x squared minus 1 right parentheses times left parentheses x squared plus 1 right parentheses. Substituting gives 2 times left parentheses x squared minus 1 right parentheses times left parentheses x squared plus 1 right parentheses minus 5x times left parentheses x squared minus 1 right parentheses equals 0. Step 4. Factor out the common group x squared minus 1. This yields left parentheses x squared minus 1 right parentheses times left bracket 2 times left parentheses x squared plus 1 right parentheses minus 5x right bracket equals 0. Distribute the 2 to get left parentheses x squared minus 1 right parentheses times left parentheses 2x squared plus 2 minus 5x right parentheses equals 0. We can rewrite the quadratic factor in standard descending order. So we have left parentheses x squared minus 1 right parentheses times left parentheses 2x squared minus 5x plus 2 right parentheses equals 0. Step 5. Apply the zero product property. If a product is 0, at least one factor must be 0. So either x squared minus 1 equals 0, or 2x squared minus 5x plus 2 equals 0. Solve the first factor. X squared minus 1 equals 0 gives x squared equals 1, so x equals plus or minus 1. Solve the second factor. We factor the quadratic. 2x squared minus 5x plus 2 equals left parentheses 2x minus 1 right parentheses times left parentheses x minus 2 right parentheses equals 0. Therefore x equals 1/2, or x equals 2. Collecting all roots, x equals negative 1, x equals 1, x equals 1/2, and x equals 2. These are all the real solutions of the given quartic. In this lesson, we will solve a symmetric or reciprocal quartic equation using a substitution. The equation is 2x to the fourth minus x cubed minus 6x squared minus x plus 2 equals 0. Notice the coefficients are symmetric. 2, -1, -6, -1, 2. This is the hallmark of a reciprocal polynomial. Step 1. Since x equals 0 is not a solution, we can safely divide the equation by x squared. Dividing everything by x squared gives 2x squared minus x minus 6 minus 1 over x plus 2 over x squared equals 0. Step 2. Group like reciprocal pairs to reveal the structure. 2 times the quantity x squared plus 1 over x squared minus the quantity x plus 1 over x minus 6 equals 0. Step 3. Use the identity x plus 1 over x. All squared equals x squared plus 2 plus 1 over x squared. So x squared plus 1 over x squared equals the square of x plus 1 over x minus 2. Substitute this into our grouped equation and simplify. Step 4. Let y equal x plus 1 over x. Then we have a quadratic. 2y squared minus y minus 10 equals 0. The discriminant is 81, so y equals 1 plus or minus 9 all over 4. Therefore y equals 5/2, or y equals -2. Step 5. Solve for x in each case. Case 1, x plus 1 over x equals 5/2. Multiply both sides by 2x to get 2x squared minus 5x plus 2 equals 0. This factors to give x equals 2 and x equals 1/2. Case 2x plus 1 over x equals -2. Multiply by x to get x squared plus 2x plus 1 equals 0, which is a perfect square. So x equals -1 with multiplicity 2. As a quick check, we can factor the polynomial completely. 2x squared minus 5x plus 2 factors as the product of 2x minus 1 and x minus 2. So the entire quartic factors as the square of x plus 1 times 2x minus 1 times x minus 2. Therefore, the solutions are x equals 2, x equals 1/2, and x equals -1 as a double root. In this lesson, we will solve a 6th-degree reciprocal equation step by step using a symmetry substitution. Here is our equation. Notice the coefficients are symmetric from the ends toward the middle. That is the hallmark of a reciprocal polynomial. Step 1. The degree is 6, which is 2 times 3. Because the degree is even, we divide the whole equation by x cubed, assuming x is not 0. We will check x equals 0 at the end. Step 2. Group like reciprocal powers together. 6 times the quantity x cubed plus 1 over x cubed, minus 5 times the quantity x squared plus 1 over x squared, minus 32 times the quantity x plus 1 over x, and then minus 10 equals 0. Step 3. Use identities to reduce powers in terms of y equals x plus 1 over x. Recall x squared plus 1 over x squared equals y squared minus 2. And x cubed plus 1 over x cubed equals y cubed minus 3y. Substituting these into our grouped equation and simplifying gives 6y cubed minus 5y squared minus 50y equals 0. Step 4. Factor out y. We get y times the quantity 6, y squared minus 5, y minus 50 equals 0. So either y equals 0 or 6y squared minus 5, y minus 50 equals 0. Using the discriminant, delta equals 25 plus 1200, which is 1225. Therefore, y equals 10 over 3, or -5 over 2, or 0. Step 5. Back substitute for x. If y equals 0, then x plus 1 over x equals 0, which implies x squared plus 1 equals 0, giving no real solutions. If y equals 10 over 3, then 3x squared minus 10x plus 3 equals 0, whose roots are x equals 3 and x equals 1/3. If y equals negative 5 over 2, then 2x squared plus 5x plus 2 equals 0, whose roots are x equals negative 2 and x equals negative 1/2. In this lesson, we will solve a fifth-degree reciprocal equation using a clean step-by-step algorithm. Our goal is to factor strategically and reduce the problem to simple quadratics. Here is the equation. X to the fifth minus 3x to the fourth minus 11x cubed plus 11x squared plus 3x minus 1 equals 0. Step 1. Notice the coefficients appear in opposite pairs, 1 and -1, -3 and 3, -11 and 11, for an odd-degree anti-symmetric coefficient pattern. X equals 1 is a root. Let's verify by direct substitution. Step 2. Since x equals 1 is a root, factor out x minus 1. We can use synthetic division with root 1 to find the quartic quotient. Step 3. Since x is not 0, divide equation 1 by x squared and group terms to reveal the pattern in x plus 1 over x. Then use the identity for x squared plus 1 over x squared equals the square of x plus 1 over x minus 2. Step 4. Let y equal x plus 1 over x. Then the equation becomes y squared minus 2y minus 15 equals 0, which factors as y minus 5 times y plus 3 equals 0. Step 5. For y equals 5, we have x plus 1 over x equals 5, which gives x squared minus 5x plus 1 equals 0. The solutions are 5 plus or minus the square root of 21 all over 2. For y equals negative 3, we have x plus 1 over x equals negative 3, which gives x squared plus 3x plus 1 equals 0. The solutions are negative 3 plus or minus the square root of 5, all over 2. Do not forget the earlier root x equals 1. Collecting all roots, the solution set is 1, 5 plus or minus square root 21 over 2 and negative 3 plus or minus square root 5 over 2. In this lesson, we will solve a rational equation using a clever substitution. We will follow a clean, step-by-step algorithm to reach the real solutions. Here is our problem. We will aim to isolate the repeating expression x plus 3 over x, then substitute a single variable to make the algebra simple. First, we divide each fraction's numerator and denominator by x. Note, x equals 0 would make the original fractions undefined, so x is not 0. This gives 4 over x plus 1 plus 3 over x, plus 5 over x minus 5 plus 3 over x, equals negative 3 over 2. Now, group the repeated pattern as left parenthesis x plus 3 over x right parenthesis, then plus or minus the constant. Let y equal x plus 3 over x. Substituting, we get 4 over y plus 1 plus 5 over y minus 5 equals negative 3 over 2. Now, we will combine the left side into a single fraction using a common denominator. We cross-multiply to clear denominators. Negative 2 times the quantity 9, y minus 15 equals 3 times the quantity y squared minus 4, y minus 5. Expanding and gathering terms gives 3, y squared plus 6, y minus 45 equals 0. Divide by 3 to simplify. We get y squared plus 2, y minus 15 equals 0. Which factors into y plus 5 times y minus 3 equals 0. So y equals negative 5, or y equals 3. Now we back substitute. Case 1, y equals negative 5. That means x plus 3 over x equals negative 5. Multiplying by x gives x squared plus 5x plus 3 equals 0. Using the quadratic formula, x equals negative 5 plus or minus the square root of 13, all over 2. Case 2, y equals 3. That leads to x plus 3 over x equals 3. Multiplying by x gives x over x equals 3. Multiplying by x gives x squared minus 3x plus 3 equals 0. The discriminant is 9 minus 12, which is negative 3, so there are no real solutions from this branch. Therefore, the real solutions are negative 5 plus the square root of 13 over 2, and negative 5 minus the square root of 13 over 2. In this lesson, we will minimize a squared plus b squared, given that the symmetric quartic equation has at least one real root. The equation is x to the fourth plus ax cubed plus bx squared plus ax plus 1 equals 0. We are told it has at least one real root. Our goal is to find the minimum value of a squared plus b squared. Step 1. Note that x equals 0 is not a root because the constant term is 1. So we may divide the equation by x squared. This gives x squared plus ax plus b plus a over x plus 1 over x squared equals 0. Step 2. Group symmetric terms and substitute. We set y equal to x plus 1 over x. Then, using the identity, x squared plus 1 over x squared equals y squared minus 2, we obtain a quadratic in y. Y squared plus ay plus b minus 2 equals 0. Step 3. For x to be real, the expression y equals x plus 1 over x must satisfy absolute value of y is at least 2. We visualize the allowed y region as everything less than or equal to -2 or greater than or equal to +2. Step 4. Solve the quadratic in y and impose the domain. The roots are y equals negative a plus or minus the square root of a squared minus 4 times b minus 2 all over 2. To have at least one allowed y, we require that the maximum absolute value of the two roots is at least 2. By the triangle inequality, this leads to absolute value of a plus the square root of a squared minus 4b plus 8 all over 2, at least 2. Simplifying gives absolute value of a is greater than or equal to 1 plus b over 2. Step 5. The minimum occurs on the boundary where the inequality is tight, that is, absolute value of a equals 1 plus b over 2. We will minimize a squared plus b squared along these two lines. Geometrically, we draw the AB plane, plot the two lines, and then find the smallest circle centered at the origin that touches either line. The tangency occurs at b equals negative 0.4 and a equals plus or minus 0.8, yielding a squared plus b squared equal to 4/5. Step 6. We confirm feasibility. At the minimizers, the y root lies exactly on the boundary. When a equals positive 0.8 and b equals negative 0.4, we have y equals negative 2, which gives x plus 1 over x equals negative 2, so x equals negative 1, a real root. When it equals negative 0.8 with the same b, we get y equals positive 2, and hence x equals 1, also a real root. So the minimum value is indeed achieved. Therefore, the minimum value of a squared plus b squared is 4/5. This occurs at a equals plus or minus 4/5, and b equals negative 2/5. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.